Properties of logarithms, more examples. Recall that a logarithm is an alternate way of writing an exponential equation. So if we have y equals b to the x, that is equivalent to x equals log base b of y. They are the exact same thing. Let's start by changing between the forms. So if we have the log base 3 of 9 equals 2, how could we write that as an exponential expression? Which should be a correct statement, of course. So notice the location of things. In the logarithmic expression, remember that the x is going to be our exponent in the exponential expression. The base in the logarithm is that subscript, but it's this position right here in the exponential. So I could do my base 3 to the exponent equals what? Well, the thing inside, in this case inside implied parentheses. And that's the way I usually say it. The base to the exponent is this thing inside. If we wanted to rewrite log base 2 of 1/8 equals -3 in exponential form, we do the base 2 to the exponent, -3, equals the thing inside, 1/8. What if we had an exponential expression to start? Say 5 squared equals 25. Then we could write this in logarithm form in the following way, saying the log base what? Well, this is the base in the exponential, so the log base 5 of my end result equals the exponent, right? The logarithm is the exponent. So 5 squared equals 25 becomes log base 5 of 25 equals 2. It's a little confusing. You just need to practice it a little bit. It is that way because we say so. There is no other reason for it. One more example. 4 to the -2 equals 1/16. I could write this as log base 4, because that's the base right there. Log base 4 of what? Well, my end result equals the exponent. Log base 4 of 1/16 equals -2. Let's look at a little bit more complicated example. And this one should be done without a calculator. I'm going to give you a couple facts, and then we are going to try to find other logarithmic values using these basic facts. So I have the log of 2 equals 0.301, roughly, it's approximately, but we'll say equals. The log of 3 equals 0.477. And I want to find some of these following values. Let's say the log of 1, the log of 4, of 5, and 6. We'll skip 7, 8, 9, and then 10. Do you know any of these right off the top of your head? Hopefully you know this first one. The log of 1 is 0. How about the log of 4? Here's one way to handle it. The log of 4 is log of 2 squared, because 4 equals 2 squared, right? So how does that help us solve this problem? Well, we can use a property of logarithms where I have something raised to the power, I can bring that power down in front and multiply it. So log of 2 squared equals 2 log 2. But I already know what the log of 2 is. It's 0.301. So 2 times the log of 2 is 0.602. Let's skip down to log of 8 and handle that in a similar fashion. The log of 8 is log of 2 cubed because 2 cubed equals 8. So using the properties of logarithms, the one with something raised to the power, where I can bring that power down in front, I get that the log of 2 cubed is 3 times the log of 2, which is 3 times 0.301 because I gave the log of 2 up top. And that equals 0.903. Now I'm going to make a mistake on the log of 5 and see if you catch this. I'm going to say that the log of 5 is a log of 2 plus a log of 3. Why is that not correct? It's a very common mistake that students make when I give them this problem. So why is that not a true statement? Well, it's not a true statement because it belongs down for the log of 6. Why is that? Well, if I wrote the log of 2 plus a log of 3 and use my properties of exponents going the other way, when we add 2 logarithms, can't we make that one log by multiplying the things? 2 times 3 equals 6. So the log of 2 plus the log of 3, using properties of logarithms correctly, is not the log of 5, but the log of 6. And if I know that, then I can use the values that I have up top to solve this. The log of 2 is 0.301. The log of 3 is 0.477. And if we put those together, we get 0.778. How about the log of 10? How do we handle this one? Well, to handle this one, I'm going to recall that when I don't have a base, it's implied base 10. So log of 10 is really log base 10 of 10. And I want to know what this equals. Since I don't know what it equals, I'll just call it x. So what does x equal? In this case, I'm going to rewrite it in exponential form, where I have the base to the exponent equals the thing inside my implied parentheses. So 10 to the x equals 10, or 10 to the first, which means x equals 1. And since I called x the log of 10, I know that the log of 10 equals 1. Why do I need that before I do the log of 5? Well, because 5 equals 10 over 2, doesn't it? And using properties of logarithms, I could subtract these two, give me the log of 10 minus the log of 2. And I know both of those values. Log of 10 is 1. Log of 2 is 0.301. And now I subtract them, I get 0.699. Finally, the log of 9. I'm going to do 9 as 3 squared and use a similar tactic that I use for log 4 and log of 8, where I can write log of 3 squared as 2 times the log of 3. where the log of 3 from above is 0.477. So 2 times 0.477 is 0.954.